Hey everyone, this is lesson 5 in unit 13. We're looking at normal distributions today. A normal distribution is a way to estimate probabilities, and the pattern is going to make a bell-shaped curve. We call that the normal curve. A standard normal curve is a curve that's centered on the y-axis, and the mean of the standard normal curve is at the 0 spot on the y-axis, and the standard deviation of the data is 1. I've highlighted some of the characteristics of a normal curve. We said the maximum value is at the mean. That's symbolized by the Greek letter mu. The standard deviation is used by the Greek letter sigma. And all the area under the curve, nearly all of it, that's 99.7%, is going to be found within 3 standard deviations of the mean. So here's our mean here in the middle on the y-axis. And 3 standard deviations in either direction is going to cover almost 100% of the data. The total area under the curve is always 1. And any area under the curve between 2 x values, so for example here and here, would correspond to the probability that the x number is between those 2 values. So we would say 34% of the data would be within 1 standard deviation, or 68% within 1 in either direction. In this first example, you can see I've already taken my histogram here, and I've kind of estimated the number for each bar in our graph to represent the heights of men ages 26 to 35. So we're going to use that table. You can use my data values or you can estimate your own. In the survey of American men, the heights are distributed normally above the mean, about the mean, and that's shown in our graph. We want to know what percent of men aged 26 to 35 are 68 to 70 inches tall. So we're going to look from here to here. And if that area represents the percent, then we could say 11%, 13.2%, and 16%, or about 40.2% of the men would be between 68 and 70 inches tall. On B, about what percent of the men in the survey are less than 70 inches tall. So without scrolling back and using the data, that would be 1 and 3, 5.8, 6, 11, and 13.2. So adding all of those up, it looks like about 40% of the men are less than 70 inches tall. Now, in Part C, suppose the survey was the data of 1,500 men. About how many men would you expect to be within the 68 to 70 inch range? So if it was 40.2%, writing 40.2 as a decimal times the 1,500 men in the survey with our calculator, that's about 603 men would be expected in that survey of 1,500 men. And Part D, the mean of the data is 70, and the standard deviation is 2.5. So we want to know about what percent of the men are within 1 standard deviation of the mean in height. So again, using our data, that's 11, 13.2, 16, 14.2, and 12. So about adding that up, that's about 66.4% of our men are within that standard deviation there. And the way we found that was to add that standard deviation to the mean of the data. So 70 plus 2.5 is where I stopped, and 70 minus 2.5 was where I started. So we started at 68 and we stopped at 72. So we would stay within that data set. For example 2, we have the table that shows the length of 40 great white sharks in feet. And we got this information from Scuba News magazine. So what I did with that ahead of time is I entered the data items into my calculator to make a histogram. And in part B, this is the recording of what I got off of my TI-84 calculator. So I entered these into a list and graphed the graph so that I could see and perform the one variable statistics test. You see I've got X bar as 15.7, so that's going to represent my mean, or mu, 15.7 feet. That's going to be in the middle. And sigma is right here, 2.5. So 2.5. Sigma is 2.5. Using that data, what I did was I found that the lowest number was 9.4 and my highest number was 22.8. And I took the sigma and I added 2.5 to 15.7, and then I subtracted 2.5 from 15.7. I'm going to go ahead and show you my normal curve below so you can see the procedure. So I started at 15.7 here in the middle, added 2.5, 2.5, and 2.5 to get 3 standard deviations, and went back and subtracted 2.5 to get 3 standard deviations. And starting at 8.2, if that's my lowest data point, in that table I noticed one data point that was between 8.2 and 10.7, which was, again, this lowest value here of 9.4. And then 22.8, that, again, was my highest value. And between 20.7 and 23.2, there was only that one data point of 22.8. So without spending a lot of time in the video, what I did was go back to that table and use all of that information, highlighting very carefully each category. For example, in the 18.2, or in the middle, 15.7 to 18.2, I had these data points. And you can see that I had 14 data points in all that fit into that category between 15.7 and 18.2. So if you use some color coding system, you should get all of our data points, 1 in the first in 3 sigma away, in 2 standard deviations, 7 data points, in 1 standard deviation, 12, going the other way, 14 data points, 5 data points, and 1 data point. It's a little tedious, but you can see how we went about figuring that graph. Then just to recap, we're going to call this the 68, 95, 99.7 rule. It's sometimes called the empirical rule. When a data set is normally distributed, about 68% falls within 1 standard deviation, and about 95% falls within 2 standard deviations. And in order to find the values that are 2 standard deviations away from the mean, we would find the values that have a z-score of plus or minus 2. So in a normal distribution with the mean of mu and the standard deviation of sigma, we call that 68, 95, and 99.7 fall within 1 standard deviation, 2 standard deviations, or 3 standard deviations from the mean. And I have a graph down here to show that representation. So 68% falls within 1 standard deviation, and 95% falls within 2 standard deviations, and about 99.7% fall within 3 standard deviations. And that's where on page 1 of our notes, we saw 34% here, 13.5% in our red region, You total that up, that adds up to 95%, and then 2.35% in that third standard deviation, which leaves these little tails of 0.15% to make 100%, 0.15. Here, using standard normal values, we're talking about a z-score here. If a random variable x is normally distributed with a mean of mu and a standard deviation of sigma, then the standard normal value of x is given by z equals x minus our mean divided by the standard deviation. The table shows the approximate area under the curve for all the values less than z for selected values of z. So if we have this table here, it's going to represent the scores on a test that were normally distributed with a mean of 76 and a standard deviation of 8. So we want to estimate the probability that a randomly selected student scored less than an 88. So we're going to calculate the z-score here. And z is x minus mu, so 88 is our x, and mu, and the mean is 76, and we're dividing by the standard deviation, that's 8. So 88 minus 76 divided by 8 is 1.5. So if we find the area under the curve for all the values that are less than 1.5, right up here, then we see that is 0.93. And these are the scores that are normally distributed. So the probability of getting an 88% on the test is about 0.93 or 93%. In part B, if we estimate the probability that a randomly selected student scored between 72 and 80, we're going to have to find two different z-scores. First, we'll say 72, so the low end, the z-score is 72 minus the mean, that was 76, divided by the standard deviation of 8. And the second z-score, let's label these z sub 1 and z sub 2, is the top end, 80 minus 76 divided by 8. So the first one is negative 1/2, and the second one is positive 1/2. So on our table again, the area that's negative 1/2 is 0.31. So let's just highlight this, 0.31, and the area that's above is 0.69. Then we got to think about the area overlapping, so we want to take the difference between those two. Let's make a note of that. So here the area is 31%, and this area, the second area, is 69%. The overlap is 0.38. So we could summarize this by saying that the probability of a score that's between 72 and 80 is about 38%. So we found where those two overlap. In this example, we see that many data sets can be modeled by a normal curve, but not all data is normally distributed symmetric like this middle term. Sometimes the tail is longer on one side than the other, and that's called a skew. Here we have a positive skew because the mean is to the right of the median, and here we have a negative skew because the mean is to the left of the median. You might want to write that down on your note. Something like this. The mean is to the right of the median, and the mean is to the left of the median. In example 4, the height of 24 children entering a theme park are shown. The mean of all the children at the park is 49 inches, and the standard deviation is 6 inches. We want to see if the data appears to be normally distributed, and then we can explain our reasoning. Now, what I did was I labeled or ordered the data in the set on some scratch paper, and I found out that the median is 49 plus 51 divided by 2. So our median was 50, but the mean, again, which I did separately, the mean was 49. I just don't want to spend time on the video doing that. So to answer our question, does the data appear to be normally distributed? And I would have to say no, that the data is skewed negatively or to the left, because there's more values above 49 inches than below 49 inches. So we could put that into a sentence. This data is skewed. So I wrote that sentence something like this. The data is negatively skewed to the left. There's more values above 49 inches than below. Or saying it another way, the mean is less than the median. And using a calculator to draw a histogram and calculate those one variable statistics, we found out that the mean was 49.2 and the standard deviation was 3.2. And here you can see I had 12 data points that were above and 10 data points that were below to help you clarify that. This is our last example in a college algebra course that has 286 students. The final exam scores had a mean of 67.5 and a standard deviation of 7.4. The grades on the exams are all whole numbers, and the grade pattern follows a normal curve. So we want to sketch a normal curve, labeling the x-axis values at 1, 2, and 3 standard deviations from the mean. So 67.5 is in the middle, and we're going to add 7.4 to each standard deviation. So you might want to turn off the video and complete your x-axis here, and then join me again. So my x-axis looks like this. We started at 67.5. Now on page 1, we know 34% fit in this first standard deviation. So if you multiply 34% times the 286 students, you'll find that there should be 97 students on one standard deviation. And then if 13.5% is in 2 standard deviations, then you would have 38.6, or we would have 39 students on either side. And then 2.35% in the third standard deviation of 286 would give us 6.7, or 7 students in both ends. Now we can draw our standard normal curve. And so my finished curve looks like this. On part B, find the number of students who receive grades from 1 to 2 standard deviations above the mean. So between 1 and 2 standard deviations, that would be our 0.135 or 13.5%. And we had already done this to draw the graph. That's 38.61, or about between 38 or 39 students. And then part C, how many students earned a grade below 60? That would be 13.5% plus 2.5%. So 13.5 plus 2.5, which is about 16%. So 16% times the total of 286 is 45.76, so about 46 students. About 46 students. earned a 60 or below. 60 or below. And I'm getting the 2.5% by taking the 2.35 and that little tail of 0.15 and getting 2.5% for this portion. This 13.5 is within 2 standard deviations. So part D, suppose the class only had 170 students. About how many students would earn a grade of 82 or more? So again, looking up at our chart, we're going to find that 82 or more would be, some data would fall within here, some would be in here, and some would be in here. So we're 2 standard deviations plus that little bit of a tail. It's going to be similar to part C. So we would have 13.5% plus a 2.35 plus the little tail of 0.15. So again, that's the 2.5%. So we're still looking at 16% of the population. So 16%, and this time there's only 170. So 16% of 170 is 27.2, which tells us that about 27 students out of 170 students, or 16% of the population, would score 82 or more. And that is the end of Lesson 5 on normal distributions. Okay, so we're going to go